downstairs lights. Nicely coordinated. Okay, Google, turn on living room lights.
Okay, turning 2 lights on.
Oh, excuse me.
Hello.
Hello. Sorry, I don't have my screen up. Oh, hi, Kevin.
Hi.
You all right?
Yeah, I just woke up a couple minutes ago.
Okay. How do you pronounce Ryan's last name?
Pfeifle.
Pfeiffe?
Pfeifle.
Pfeifle. Okay.
Yes.
Yeah, I don't butcher that.
That's a
Ian
good one
names.
to check beforehand.
Yes. Pfeifle. All right. Looks like we're going to have a closed zone.
I was just going to check the weather.
Yeah, it seems to be mostly cloudy. I can't really tell from my window.
Yeah, probably.
I need to switch that setting. All right. Shush. You don't usually talk to me, Cindy. What's wrong?
Oh, I see he's in the waiting room. I'll let him in, I guess.
Oh, yeah, please do.
Hello.
Hello.
All right.
How are you guys?
Doing all right. How about you?
Yeah.
Not too bad. Hanging in there.
So the first thing I want to do is I want to verify your last name or how it's pronounced. It's Pfeifle?
Yep.
All right, sweet.
Yep. Awesome.
And is that from background from Rogue One?
It probably is. Yeah, actually. I have a bunch of Star Wars virtual backgrounds. This probably was Rogue One.
Okay. Let's see. Let's make you a co-host. So if you want to, whenever you're ready, if you want to try sharing your screen, you can do that.
Sure. Cursor. All right. I'm wondering if you're seeing the correct screen. Are you
hunting elusive giants?
okay? Are you seeing the regular slide, or are you seeing like the slide?
I am not seeing presenter view.
Okay. Okay. All right. Cool. Awesome. So I'm gonna click through. You can see all that.
Yep.
Yeah.
Okay. Awesome.
Nice.
Great.
I always love AGN talks. Really pretty pictures.
Yeah, that's. I try to throw in as many as I can. I'll stop the share for now. Yeah, there is no end to the pretty pictures. I long for the day where Exoplanet Talks will have such high resolution that we can have
more than a
That would
pixel.
be awesome.
Yeah. I will settle for the ALMA pictures nowadays, though. Those ones.
Yeah,
are pretty
there's some pretty
spectacular.
cool direct imaging pictures now, but I'm pretty sure it maxes out at something like 10 pixels for a planet.
Yeah, yeah. Just popped up on my Facebook this morning. Was one of the studies from July where they think that they have like an exomoon forming in a planetary protoplanetary disk, and I was like, why is this popping up now? This was something that was news 5 months ago, because I got all excited, and then I ran into the other room to tell Natasha. She was like, yeah, but we knew about this. And I was like, oh, that's right, we did know about this. Because I had the same reaction 5 months ago when I first saw the paper.
I think we actually had the PI on that give us a talk, but I can't, for the life of me, I can't can't remember his name.
Wow. That's awesome.
Would that have been David Kipping? I know he's the big exomoon guy.
I think he might have been on the paper, or at least on the paper. It might have been his. I'm not sure. I thought he was a theorist.
I mean, yes, I think so in general, but I don't. He seems like he gets up to a lot of stuff.
This is true.
Hey, Em.
Hello.
Yeah.
Nice, very squeaky chair. So we'll start in about 5 minutes or so.
Sure.
There we go. Thank you for being early. Normally our speakers we're trying to scramble to find out where our speakers are right about now. So thank you for being here early.
Yeah.
Yeah, I checked in with Kevin earlier, and I was like, yeah, when should I show up?
Yeah, I almost
So I
told
was
you, like the last speaker showed up at like 7:03. So like it's but yeah, early is better for everyone.
Yeah, I was giving comments on a paper, and then I was like, oh crap, I need to eat food real quick, and I was like wolfing my food down. That's like, I better get this done beforehand. It should be good. How many people usually show up?
It varies, but I guess close to, I feel like 25 is a normal-ish number, but it's sometimes higher, I guess.
I will say that one of my assignments for my class is to attend one of these, and there's only 2 left, so I imagine we will have a larger than average crowd tonight.
Gotcha.
But
Cool.
given how many people are in the 10, all right, so there's 10 in the waiting room at the moment. 11.
Yeah, most of them show up within the first 5 minutes of it starting.
Yeah,
So
the last
most
second.
people aren't early necessarily.
Yeah. Oh, hang on. That's my dog. What are you barking about?
Oh, wow, he actually looks like he's walking down the hall. That's
Yeah, it got pretty far back before the green screen popped out.
yeah.
And then I just stroll in from the side. Wonderful. I have a bunch of these too, which is hilarious. This is the one I've been using lately, but I've got some stormtroopers, different stormtrooper ones.
Nice.
Got an X-wing one. I got to find more. A buddy of mine has one. He goes out of his way to find distracting Zoom backgrounds for all of his meetings, and he's got one where like stormtroopers are dancing behind him, and he's gotten messages in meetings where they're like, "Dude, you got to turn that off. I can't focus." It's too good.
Bring up my. Speaking of slides, let me bring up mine. Is this the right deck? Yes. $11. All right.
Oh, so today we have closed dome tour instead of open dome, and what should we focus on?
Looks real cloudy. Obviously for the objects, we'll just primarily focus on galaxies, I suppose.
Okay.
Seems like the thing to do.
I put a few of, or at least I hope so. I put I intended to put a few of Owen's galaxy images in the tours folder. So I think we should have one of his for the starburst, and we should have another one for fireworks, and there's I can't remember it's the one with the giant poster in the control room. I can't remember the name of that.
Cigar galaxy.
Cigar.
Oh yeah, cigar.
Those are pretty good.
I saw a few new ones up on the observatory webpage. They were pretty cool. There were a few new nebulae and a couple new galaxies. Always fun to see.
We do have an image of one of the Abell clusters, but it's not overly impressive. You really kind of need to know what you're looking at in order to appreciate it.
I think they just went for it because it was really far away.
Yeah.
Yeah.
Well, all right. I guess we'll start letting people in.
All right. Let me.
Oh yeah, share your slide
screen
first.
and all
I guess
that kind of good stuff.
Yeah.
Where is Zoom? Where's Zoom? I have way too many screens up. Way too many screens. Let's do that. Oh, Ryan, if I will be sharing my screen first, since I have a little bit of slides to
intro.
Let's see. Okay.
All right, I'll let them in.
Yeah, bring them on in. Yeah, that's one of my students right there. All right, welcome everyone to the George Mason Observatory Evening Under the Stars. I will preface this by saying that unfortunately, due to the weather, we are going to be showing a closed dome tour, but please feel free to hang around, particularly if you're any of my students. This will count for that assignment. We will be showing, as complimentary to our excellent speaker tonight, we will be showing images taken by a few students here at GMU of galaxies, a couple of them actually interacting galaxies. But before I really get into that, I'd like to give you a brief introduction to our observatory, assuming that I can tech. There we go. Here are the observatory. If you've been on campus, the observatory is on the top of Research Hall, basically that nice silver tower. Our observatory 32-inch telescope is located at the top. The arrow is pointing to the control room, which during the before times, we actually observed, we controlled the telescope from this control room. And we still do on the occasion. We can now virtually dial in and control the telescope from there. The images that you see are some of the images taken by GMU students over the years of various astronomical objects, from the Orion Nebula to the Whirlpool Galaxy to the Ring Nebula. And so we have a very active student organization, which I'll talk about in a moment, but who contribute to these pictures that we have. Evening Under the Stars are every alternating Thursdays, starting at 7. The next one and last one is on December 2nd. We will have a friend of mine, Noel Richardson, as our speaker. He will be talking more than likely about Eta Carina, the star that has obsessed his life thus far. Evening Under the Stars usually go from 30 to 45 minutes in terms of the public talk at the beginning, and then we follow that up with a 30 to 45-minute guided tour of the night sky, if it's clear, or of images that we've taken, and potentially highlighting some of the research that we've done here at JMU afterward. If you'd like to know more about the observatory specifically and how the observatory is utilized, I highly encourage you to sign up for the Moon, or the Mason Observatory Outreach newsletter that you can see on the website. We have articles contributed by the observatory staff that highlight, like I said, the research that we do, the students who do the research, and also just astronomical events and space exploration events that are currently in the news. If you're really impressed by what we see here, or you're just looking for a philanthropic angle that is astronomy focused, please feel free to become a patron of our observatory. We are greatly expanding our outreach and our teaching and research arms. And in order to do that, in order to help do that, funds would be greatly appreciated. Any support that we get, particularly just participation from the local community and students within the community, is very much appreciated. However, funds go a long way in helping us have people who are there to engage with the public for outreach events beyond the university. You can donate at various different levels, from star all the way up to Big Bang. Here are a few of our list of our current patrons. And so please, as I said, we are very, very thankful that you are here tonight. But if you feel that if you can give a little bit more, please support our patron initiative. As in terms of the observatory, this is not a one-person show. We have a number of people behind the scenes, including myself, Dr. Rob Parks. I am the Deputy Director of the Observatory. Dr. Peter Plavchan, the Director, is currently in attendance. After the public event, you will be guided through your public tour by Kevin Collins and Thunyapong. I believe I am massacring that name correctly. And in terms of the student organization, that is Jonathan. He is running a very active student organization right now. So if you're interested in joining and learning more about astronomy, or just socializing with astronomically minded students, please feel free to look up Photo or Friends of the Observatory Student Organization on the web, and I'm sure you'll find more information. Or you can contact us via the website, or we are also active on Twitter at GMU Observatory, or you can email us specifically at the below website. Now for the main event, we have Ryan, who is a fifth-year PhD candidate at George Mason. He works with X-ray observatories. Some of the more impressive X-ray observatories are including Chandra and XMM Newton. These are the grand observatories of NASA, and particularly in the space regime. I have to admit, I would not have the patience for doing X-ray observing, because it has to be space bound. You cannot do really X-rays from the ground, and so they are starved for data, from my understanding. He specifically is using the X-rays to study dual AGN, or active galactic nuclei. I'll let Ryan talk more about what that means, but he's basically studying large-scale galactic mergers and looking at the interactions of their cores and how a tremendous amount of energy is generated. He is a recipient of several awards, including the Sigma Chi Grant in Aid of Research, and has received competitive international travel grants, as well as a summer research grant offered here through the Department of Physics and Astronomy. So without further ado, I will pass it on to Ryan, and I will stop sharing my screen.
All right, well, thank you very much. Let me go ahead and share my screen now. All right, everyone can see that? Is that a yes?
Mm-hmm.
Okay, awesome. Great. My name, like Dr. Parks said, is Ryan Pfeifle. I'm a fifth-year PhD candidate here at George Mason. I was also here for my undergraduate degree, so I have a bachelor's from Mason, and I will, by the spring, I'll have a PhD from here as well. Like Dr. Parks mentioned, I am an X-ray astronomer. So my primary expertise is using X-ray telescopes to study supermassive black holes at the centers of other galaxies. And so today I'm going to talk about a fun topic, some work that I led a couple of years ago now, before the dark times, which is encompassed in this title, Hunting Elusive Giants, uncovering a triplet of active galactic nuclei in a galaxy merger. And so this galaxy merger is this object actually here. And so what I mean by galaxy merger is literally the coalescence, the collision of two galaxies that will eventually become one. And so this was work that a lot of my colleagues and I worked on from a variety of institutions, both domestic and international. So it was a very large amount of work. I'm very happy to be here talking about this today. So for those who don't know what an AGN is, an AGN is an active galactic nucleus. That's a code word for a feeding supermassive black hole. So at the centers of most massive galaxies, we have very good evidence that suggests that there are supermassive black holes residing in the nuclear or the center regions of these galaxies, and they get to have masses of about a few hundred million to a few billion times the mass of our sun. If you dropped these objects at the center of our solar system, they're so large that they would go out to about the orbit of Pluto. These are gigantic objects. And that's what's powering what we call an active galactic nucleus, which is when material is falling onto the black hole. The black hole is feeding and growing in mass. And as this material falls towards the black hole, the material is rubbing against itself, so molecules rubbing against molecules, and is being heated up as it falls towards the black hole. And you start to get emission across the entire electromagnetic spectrum. So from the optical, which is what we see, to heat wavelengths, which is the infrared, radio, X-rays, and gamma rays. So that's really what an AGN is this supermassive black hole that's feeding on material. Now, how do these things get to be that massive? How do you get a billion solar mass black hole at this stage in the timeline of the universe? We're actually not sure. We've looked at models, we've looked at observations. You would have to have these black holes feeding rapidly, almost non-stop, for the entire period of the universe's existence to get to that mass. Which is a problem because not everything is perfect, right? Not everything is efficient. So how do you get these black holes to be so big? How do you fuel them efficiently? Well, one thing that might allow for that is the collision of galaxies. So it's this AGN merger connection. Galaxy mergers, simulations have shown, are actually very, very efficient at driving very large quantities of gas and dust not like what we're used to, but silicate grains towards the centers of the galaxies. And this is through gravitational interactions. So I have a simulation here, which shows, let's see if it'll work. This is a simulation of two gas-rich major mergers, gas-rich major galaxies. So they're massive galaxies. The color at the beginning is messed up, but you'll get the full effect after it starts to fix itself. So what's happening is that the galaxies are moving towards each other on a collision trajectory. They intersect with one another. And here's the correct version. And you can see the gravitational interactions between the two galaxies stretch and contort the spiral arms. The colors here indicate the gas temperatures. So you can see the bluer colors out here are cooler, and the hotter gas is towards the nuclear cores. So these are the centers of the galaxies. This is fueling the AGNs at the centers. And you can see how the gas is sort of being funneled in towards the centers as this merger progresses and the galaxies eventually coalesce to become one galaxy like now. So the main takeaway is that galaxy collisions are very efficient processes at driving gas towards the centers of the galaxies, which is exactly what you need to fuel these black holes. So we have a process that might help us drive the gas, and we have these black holes. So if you get this gas within the vicinity of the supermassive black holes, it's likely going to be feeding your objects. So in a merger of galaxies, then I told you that supermassive black holes exist at the centers of most massive galaxies. So if you're colliding two galaxies together, it makes sense that there's probably two supermassive black holes in that system. And so a natural consequence of these galaxy collisions is that you could have both of the supermassive black holes lighting up as AGN, which is what we call a dual AGN. It just means there's two AGNs in a particular system. These objects are very rare, and that's because gas accretion, which is another word for the fueling of these AGNs, it's the act of the gas being consumed by the black holes. This is a double-edged sword. So you're feeding the black hole with this gas, but there's so much gas in these mergers that you actually start to block a lot of the light that's being given off by the very material that's feeding the black hole. So just like this cartoon shows, you start to actually block the emission you're actually looking for because there's just so much material, which is great for the black hole. It's an efficient environment to feed them and grow them to massive sizes, but we can't really see them very effectively. But these clouds do absorb the higher energy light, so optical, ultraviolet, X-rays, and they re-radiate this energy. They absorb it and re-radiate at heat wavelengths, at the infrared wavelengths. And so if you have an infrared telescope then, what you'd want to do is go and look for systems that are glowing intensely in the mid-infrared and the infrared, because that's probably where these systems are. They're probably enshrouded in this gas and dust that's glowing very intensely at heat wavelengths. So this is what we did. We assembled a galaxy merger sample looking for dual AGNs, and we selected it based on how intense the mid-infrared emission was in these systems, with the hopes that we would uncover these dual AGNs. Now, one particular system that we happened to include in this galaxy merger sample was this system here, which has sort of a phone book looking name. It's we refer to it as its coordinates. So, you know, if you look this up online, you'll see J0849. I'll just refer to this as the triple throughout the talk. So the triple merger or the triple black hole. So this galaxy, you can see there's a primary galaxy here with a very bright core. There's a secondary galaxy with a spiral arm with a core here. And there's a third galaxy with a third arm coming in this way. Now, when we first selected this sample, we didn't control for how many galaxies there were. We were just interested if there was more than one. We were interested if there was an active merger. And so we selected this galaxy. This is a Hubble image. This is a colorized image from Hubble that NASA made for me once this was published. And what we did, like I mentioned, is that we went and we pre-selected these galaxy mergers using the mid-infrared. We looked to see if these systems were glowing intensely in the infrared at heat wavelengths. So we used the Wide Field Infrared Survey Explorer, which is otherwise known as WISE, which did an all-sky survey of the entire sky, looking for mid-infrared sources. And this is one of those sources where it happened to have extremely red colors. We followed this up with the Chandra X-ray telescope. Hang on. Oop, punchline. We followed this up with the Chandra X-ray telescope, which is this facility here. Chandra looks, of course, at the X-ray regime, so things that we can't see with our eyes, but we're very familiar with X-rays. You go to the dental office, you get X-rays of your teeth, or you break your leg, you get X-rays of your bones. We're somewhat familiar with this wavelength regime. They're just very high energy photons. So we looked with Chandra, and we're expecting, you know, one or two sources, two if it's a dual AGN. And what we found was this much more complex system where there was not just one or two, but there were three X-ray sources. And these X-ray sources were coincident with the nuclei of the galaxies in this merger. So this was a very strange thing. And I sort of sat on this for a few days. I went and talked to my advisor, went back to the data, and we weren't really sure where to go with this. And so this started basically a 2-year adventure to obtain more data to figure out what's going on here. Because the first thing that came to my mind was, well, maybe there's 3 AGNs. But that has never been confirmed before in the literature, so we needed some extraordinary data. We then went to the NuSTAR telescope. The NuSTAR telescope stands for the Nuclear Spectroscopic Telescope Array, and that operates in the what we call hard X-rays. It's just a higher energy X-ray photon than what you observe with Chandra. And the nice thing is that the higher energy X-rays pierce through the gas and the dust much more easily than the X-rays I was looking at with Chandra. And so, and NuSTAR is very, very good for looking at AGNs, which we call heavily obscured, which is when all this gas and dust is surrounding them. And NuSTAR, in concert with Chandra, showed that there was indeed very, very high columns of gas and dust, at least around the central nucleus, the central AGN in this system. So we do have evidence that the theory is correct in this case. So this merger is funneling vast quantities of gas towards these black holes. But this doesn't really tell us about how many black holes there are. So we have the X-ray evidence. So then we turn back to the optical, so we said, okay, we have this X-ray evidence. What do the other wavelength regimes tell us? So we turn to what's called spectroscopy, which some of you may know what this is. Some of you, this may be a new concept. Spectroscopy you can think of as the fingerprints of astrophysics. So spectroscopy, everyone has done the little experiment where, when you were a kid or maybe in school, where you have a prism and you shine some sunlight through it and you break the light into the rainbow. Well, this is essentially what we do when we're doing spectroscopy. We have very much more complicated instruments on board our telescopes, but we're using these instruments on our telescopes to break the light that we're seeing up into specific wavelength ranges, specific light ranges, to better understand the physics of what's going on. And so here you can see in the optical, you can go from the red all the way to the violet, and so that's essentially what we turned to, was the optical wavelengths. So this is what we call a spectrum. So this is exactly what you get when you break the light into what we call spectra, using these essentially prisms or grisms. And so what this is showing you is the wavelength is on the x-axis. This is the this is essentially the specific energy of the light you're looking at. And here, this is essentially the amount of light you're getting per second from that particular energy. What we call emission lines, these are specific atomic transitions. So these are specific elements that you're looking at that happen to be in these gas clouds, that happen to be energized, and they're releasing photons as they try to go back to what we call their rest energy. They want to be in equilibrium, they want to be at rest. So they're releasing photons after being excited, and these are the photons we're seeing. So these are our fingerprints, are these emission lines. So what we did was we said, okay, let's go to the optical. We know we have these telltale signs, these fingerprints for AGNs. So we turned to the Sloan Digital Sky Survey, which is this telescope up here, and the Large Binocular Telescope, which is the binocular-looking telescope at the bottom. And we wanted to figure out, okay, what sort of fingerprints are we seeing here? Are we seeing AGNs? Are we seeing signatures of star formation? Are we seeing a combination of both? What's going on here? So we turned to a colleague of mine who is now has her PhD, but at the time was a fifth-year PhD student at University of California, Riverside. That's Dr. Christina Manzano King. We handed her our optical spectra, and she went through. She had a fantastic code that went through and fit these emission lines to derive what sort of physical processes are occurring in these systems. And what she found in each case was that the emission in each nucleus was consistent with that being driven by an active galactic nucleus. So this was the first time we're seeing, not only in the X-rays, but also in the optical, signatures for a triple AGN system. What she also found was that these AGNs, on top of feeding on material, they are actually feeding on so much material and they're giving off so much light that the light itself is acting like billiard balls and pushing material away from it, which was what we call an outflow. And so these velocities are on the order of 1,300 to 1,600 kilometers per second. So keep in mind, the radius of the Earth is like 6,700 kilometers. So at these speeds, you can traverse the Earth in less than 5 seconds, or less than 6. So these are incredible speeds that these clouds of gas are being driven away from the black hole. And so it's a very complicated system because you can have both the black hole consuming material, but this material, it's glowing hot. It's also, the photons are blowing material away, which is what we call these outflows. So very chaotic kinematics of the system. My colleague, who is also now Dr. Remington O. Sexton, he was also at Riverside. He was a 5th-year PhD candidate. And he also had this wonderful code that could look at the spectra and tell us if the gas and the stars in the systems seem to be kinematically coupled, which is to say that they seem to have the similar velocities. They seem to be distinct regions. And what he found was that in each case, the 3 nuclei were indeed distinct regions. We weren't worried about there being fewer than 2 nuclei at this point. We were sure that there were 3 distinct emission regions. And this is, like I said, the speeds of the gas and the stars are distinct and similar, statistically speaking. So that was a good sign. So we have this great evidence, and so we said, well, we also have other data. We have near-infrared observations, which is a little bit further in wavelength than what we used to select the system. So we turned again to the Large Binocular Telescope. We got these near-infrared spectroscopic observations. And I handed this off to a colleague of mine who is also now Dr. Jenna Can, who's at NASA Goddard. She was at George Mason with me and just graduated with her PhD this past year. And so she looked at the near-infrared spectra and found, once again, more signatures of AGN activity, these fingerprints of AGN in the system. So specifically in the primary nucleus, which was the brightest of the 3 AGN. One colleague of ours, who was actually an undergraduate at the time, and I believe she's graduated now, this is Jenna B. Harvey at James Madison. She, along with her advisor, Anka Konstantin, they looked at the near-infrared spectra for us as well. And what they found was what we call broad line regions. This is essentially when you have emission lines that, like the name suggests, are very broad in width. This is indicative of bulk motions of gas moving at high velocities. And so what it actually means is that there's these vast gas clouds moving around the black holes at incredible speeds. So they're gravitationally bound. They're not being pushed away like outflows. This is the material that's falling directly into the black hole. And the speeds of this gas are immense, above 2,400 kilometers per second, which, harkening back to the analogy to the Earth, you could traverse the Earth in less than 3 seconds. The entire width, or entire diameter of the Earth. I hope that I didn't mix up the radius of the Earth with the diameter. Sorry, getting a little jumbled. But still to the point, we're seeing these direct signatures of these bulk motion clouds. And these are smoking gun signatures for AGNs. So this is very, very good evidence that we had multiple AGNs in the system. So very, very exciting. And so, this was a whole lot to throw at you. I threw X-rays and optical and near infrared and mid infrared. There's all of this stuff. So let me just summarize here. What exactly went on with these 3 systems. So, and yes, I did spend multiple hours working on this. I also used it in a separate presentation. Essentially, here's the summary for this system. You have 3 massive galaxies smashing into each other at the same time. At the cores of each of these galaxies, we have evidence to suggest that there are supermassive black holes in each nucleus that are actively accreting material, which constitutes a triple active galactic nucleus system. We have 3 X-ray sources We have near-infrared evidence for at least 2 of these AGNs. We have optical evidence for 3 AGNs. And we have evidence showing dramatic evidence of what we call feedback, which are the outflows from these galaxies. And outflows are very important because they can actually have dramatic effects on the galaxies themselves. They can push gas clouds and either enhance star formation, or in some cases can curtail star formation, because stars, of course, condense from these cool gas clouds in the galaxies. So this is a very chaotic system with a lot of stuff going on. And I'll just sort of play this fun slide again. And so you might wonder, okay, you found a triple AGN, big deal. What's the big deal? Well, we've never actually confirmed a triple AGN in literature before now. So this was the first confirmed case in the literature, since we started studying multiple AGN systems about 30 to 40 years ago. So this was a really, really important discovery because it's such a rare object. And on top of that, this is a very local system. In relation to the size of the universe, this is very local. It's about a billion light years away, which sounds very large, but the universe is 13.8 billion years old. So there's objects that are much, much further away. And earlier in the timeline of the universe, we believe, and there's evidence to suggest, that galaxy mergers were far more common, and especially multi-mergers. So it's actually been shown in simulations that pairs of black holes, once a galaxy collides and black holes get very close to one another, on average, like 16% of the time, a third black hole or a third galaxy will collide with the resultant galaxy that had collided before and introduce a third black hole. And so these are rather significant fractions. 16% sounds small, but in the grand scheme of things, it's actually a non-negligible fraction of these systems. And triple black hole systems are actually, it's possible that they could help drive the coalescence of the black holes on a faster timeline. So it takes a long time for these black holes to shrink from the respective cores down to the centers of the resultant galaxy. And which actually, let me just scroll back here so I can show you what I mean. So if I play this video again, as this galaxy merger evolves and goes on over time, you can see that the nuclei are getting closer and closer together, and the system is eventually going to coalesce into a single galaxy. And about here, you still have 2 black holes. You have still the bright cores. They're rotating around each other, getting closer and closer, and eventually they collide. The introduction of a third black hole allows for instabilities in the orbits of the black holes and can not only increase the speed at which this process happens, but it can also lead to ejections of black holes, meaning you can have supermassive black holes wandering within the remnant galaxy itself, or slow shot out of the galaxy completely, and they're just wandering off by themselves. So these are fantastic laboratories for just phenomenal physics, which we really haven't had a chance to study yet because we just haven't found it. But with the discovery here that we had, we believe that we should be able to select and follow up and identify further cases of triple AGNs. One of my colleagues in the field has recently tried to do this using a different technique. But triple galaxies are quite important. And like I said, especially back earlier in time, when galaxy mergers were more common and multi-mergers were more common, you probably had a lot more of these triple mergers happening. And so these local laboratories help us to investigate these higher redshift systems. So I have some more slides talking about a press release that are funny and talking about the process for publication. But I don't want to take up too much time if I don't have it. I think I've run for about 20 minutes or so now. I just wanted to give a big thank you to the JMU Observatory and for Kevin Collins, who invited me, Dr. Rob Parks for the wonderful introduction. And thank you so very much for listening. I will open it up for questions. And if you have any, I'd be happy to answer them. I know it's a lot of material, so please feel free to ask me any question. There's no such thing as a dumb question.
Thank you. And if we could have a symbolic round of applause from our audience, that would be great. Thank you, Ryan, for for an excellent talk. It's been a while since I've heard an excellent AGN talk, so thank you very much. That's a good thing for treat for me, to be honest. So the first question, I'm going to take the host's prerogative and ask the first question, which is more of a general AGN question. Basically, the idea or do AGN turn off and on? And as a corollary, will the Milky Way galaxy, will our own galaxy ever become an AGN?
Great questions. So AGNs do what some people will say flicker. They do turn off and on. So the average lifetime of an AGN, based just on some back of the envelope calculations, you can sort of estimate how much gas might fall towards a black hole at any point in time. And so the average lifetime, for your average black hole, regardless of whether it's an merger or if it's an isolated system, the average lifetime is a few million years to a few tens of millions of years, maybe even 100 million. So it sounds like it's certainly long as far as human timescales go, but on the timescale of the universe, we're talking maybe a few percent or a few tenths of a percent of the timeline of the universe. So they do flicker on and off as material comes close, it falls into them. But I do want to just specify for those unfamiliar with black holes is that they don't suck material in. Black holes are, they act like any other gravitating body. So if I were to snap my finger and turn the sun into a black hole, we would continue orbiting as if nothing had happened. The only difference that we would notice is that it would be very cold and inhospitable because there's no sunlight. So black holes act the same way. What happens is that these gas clouds, as they're being driven towards the center, are on unstable orbits, or the orbits allow them to drift too close and they happen to fall into the black hole, basically. So to the second question, will our Milky Way supermassive black hole ever experience an AGN period? That is an excellent question. So it's fairly quiescent right now. There's not a lot of activity going on. I think there was a report a couple of years ago where a gas cloud actually did fall in, or maybe had a near miss with it. But as far as on human timescales, I don't think that we have any evidence to suggest that it's going to turn on and become this super bright AGN anytime soon. Just because there isn't a vast quantity of gas moving towards it. One interesting question that I would have is that if it were to turn on, how that might affect the planetary systems around it, how it might affect our system, depending on perhaps its luminosity. People have sort of done that for fun before. They've looked at systems where you have these incredibly bright AGNs that are putting out tons of X-ray emission and gamma ray emission and stuff. And I've questioned, about the habitability of exoplanet systems in those other galaxies. So it's sort of a fun sort of thing to talk about or think about, I should say. But as far as ours, I don't think so. Certainly not on human timescales.
Okay. Yeah, I had a supervisor back when I was working at Emory University, and he had a small catalog of fun ways to die in the universe. And so I was wondering if that was going to be one of the things to add to that list. As a follow-up question from Jonathan, he asks, where do the gas clouds come from, these gas clouds that fall into the AGN?
Where do they come from?
Where do they come from?
That's a great question. So in our galaxies, and it's the same with our galaxy, you have these vast quantities of gas and dust that are existing in the spiral arms. So if anyone's seen images of spiral galaxies, which let me go back here, so here, all of these blue and white pinpoints of light, these are active star forming regions. So the blue is coming from younger stars, and this brown is galactic gas and dust, which is it's dark because it's absorbing light and it's blocking light behind it. And so this gas exists intrinsically in the galaxies. So as the galaxies sort of formed in the early universe, they formed from large amounts of gas in the primordial universe. And so this gas exists in the galaxies themselves. But the process of merging, at least in the case of merging galaxies, there are other processes that can drive gas to the centers where the black holes are. But the merger process of galaxies, you have what's called tidal torques that arise in these galaxy mergers, where essentially you have the gas being funneled into a bar-like structure, and gravitational, what we call perturbations or instabilities, help to funnel the gas along this bar down into the center regions of the galaxies. And so there's not really a bar here that I don't see, but you can sort of imagine, the gas sort of being funneled down along the spiral arms into the nuclear region here. In fact, let me see. Actually, this simulation actually does show bar structure, which this is a great question because it really goes into the physics. If you look really closely here, you can see sort of an elongated structure in this nuclear region. And this is, of course, the gas that I'm showing you here. So you can sort of see there's a bar forming. It's getting sort of elongated, and it's allowing the gas to be funneled down into the nuclear regions. So it's sort of a complex physical process. I say complex, but it's really just gravity. But you have these basically gravity instabilities that help to drive the gas from the outer regions of the galaxies into the central cores.
Excellent, excellent. One of our first questions was, and I don't know what your familiarity with our telescope is. I'm assuming you have used it at some point, but the question is, can you see the triple system using our 32-inch telescope here at GMU?
So that's a good question. The short answer is yes. I haven't tried to before. I've taken some images in the past, but I haven't tried to take an image of this one. And the only reason is that you could see it, but it wouldn't be a very good detail. So I wish that I had the Sloan Digital Sky Survey image here, because then I could show you what it looks like based on the imaging we used originally. That's kind of a blunder on my part. But if I show an image of this system here, this is the Hubble image. This is fantastic resolution from the Hubble Space Telescope in orbit. And our observatory is about 0.8 meters. So it's a little less than half the size of Hubble. Hubble has a 2 meter aperture. So the detail we would get for this system is really much lower than what we had here or what we have with the Sloan Digital Sky Survey imaging. So we could see it. It just would be hard to tell exactly what it is, probably at the distance that it's at.
So do you think that we would be able to see the actual, would we be able to resolve the individual nuclei? I probably doubt it. It would just look like a fuzzy blob.
Yeah, I think it would be a fuzzy blob. You'd probably see the tidal features. It'd probably look triangular in shape. That's the Sloan Digital Sky Survey imaging actually does show a triangular shape, and you can sort of see the nuclei. But any lower resolution, you probably lose the nuclei altogether. Yeah, it would probably look more like trying to think of a different telescope at a similar resolution. But yeah, you probably lose almost all detail except for the tidal features that are really stretched out towards the edges.
William asked a question which you may have answered in the talk, so forgive me if you did, but the questions that he has are, did you find outflowing material in all three nuclei? And did you find these outflow signatures only in the optical?
Great question. So in for the outflows, we did find them in the optical alone. Now, that's not to say there aren't outflows in the near infrared. Basically what we found was that the widths of the lines in the near infrared were far away in excess of anything we saw in the optical. And they were consistent with being what we call broadline regions, which are these fast-moving gas clouds around the black holes. But it's still possible that there are signatures in the near infrared. It's just hard to discern, when you have these broadline regions. But in the optical, we saw evidence for outflows in at least 2 nuclei. And there was some signature of a possible blue shift in the third nucleus. We didn't necessarily say that was an inflow because it wasn't entirely clear. The uncertainty on that was, the uncertainties weren't good enough to state statistically whether it was a true inflow or if maybe it was just, a residual of the fit. But the other 2, we were pretty sure there were outflowing material in at least 2 of the nuclei.
We have another question asking about from Tiffany, who asks, how much more difficult does it get to, or how much more difficult does it become to detect multi-AGN further away? And as a sort of corollary to that, what are your thoughts on the LISA mission?
Great question. Hi, Tiffany. Tiffany and I knew each other from, I was an undergrad and she was at GMU for grad school. So it's been nice to see a familiar face. Great questions. So how difficult does it get to become detect? Does it, so multi-AGNs, so they're difficult to detect just generally, but as you know, but as you get further away, the problem becomes, especially in these what we call late stage mergers, where the nuclei are very close together, you start to have an issue with resolution. And so with Chandra, in the X-rays, we have a resolution of about 1.5 arc seconds, which for those unfamiliar with arc seconds, that's just the spatial scale on the sky as we see it with our instrument. So that's the closest separation we can discern before objects start to blend together. And so with Chandra, 1.5 arc seconds at this redshift, that's about 2 kiloparsecs. So about for those not learned in kiloparsecs, a kiloparsec is 1,000 parsecs, and a parsec is about 3.2 light years, 3.3 light years. So about 30,000 light years apart is where these nuclei are. So once you push it further and further out, you start to lose your resolution in the X-rays. So you really can't search for spatially resolved X-ray sources anymore. And you have a similar issue in the optical and near infrared. So the optical near infrared, not with adaptive optic systems, you can push like a few tenths of an arc second, which is great. It's better than Hubble actually. So you can push it out to higher redshift. But even then, without larger aperture telescopes, such as like the Vera Rubin Observatory, which will push, I guess that'll push about an arc second or less. But without larger space-based arrays, it's pretty hard to find these things further out in space. Really what you need is high spatial resolution, very long baseline interferometry with radio telescopes. So those allow you to push like milli-arc second scales, so you're literally probing the 30 light year or less scale for these systems, and that's at the point where they're basically gravitationally bound. Their orbit, the black holes are not in the galaxies. The galaxy is basically merged, and you're actually probing the motion of the black holes around each other at that point. So I think radio is probably the way to go. There is a multi-merger out at like redshift of 4, which is like way back in the past universe. There's like it's like a 5 or 6 galaxy system that they observed with ALMA, which is a sub-millimeter array in the Atacama Desert. And that was just a fantastic multi-merger system with a lot of stuff going on, very gas rich. So I think sub-millimeter and radio is really the best way to go as far as finding these systems further out in time. And that was a long-winded explanation. As for LISA, so those probably most people don't know what LISA is, but LISA stands for the Laser Interferometer Space Array. And so this is a mission concept that's in development between NASA and ESO and a few other space partners. And so LISA is like what we have on the ground, which is LIGO. LIGO is the Laser Interferometer.
Gravitational Wave Observatory.
Thank you. I wanted to say geospatial, and I was like, that's not right. Gravitational Wave Observatory. So LIGO has been basically looking for gravitational wave signals from stellar mass black holes. So these are, like it sounds, black holes with masses of about a stellar mass or so that are colliding. And when they collide and on their in spiral towards each other, they are actually warping space-time, and we can actually detect these ripples in space-time with these interferometers, these laser systems. LISA is a system that's going to be hopefully in the 2030s launched into orbit, and we'll be looking for not stellar mass black holes, but what we call intermediate mass black holes. So these are 10,000 solar mass to 100,000 solar mass black holes. And it'll be looking for these black holes as they, collide together. And this is very important because back in the early universe, you didn't have what we call supermassive black holes. You had intermediate mass black holes because they were in the process of growing. So as you look further back in time, the galaxies were less massive, the black holes were less massive, and they had to grow over time. So probing these intermediate mass black hole collisions will tell us a lot about how often galaxy mergers were happening. It'll tell us a lot about the collisional growth, or what we call the hierarchical growth of black holes, which we really don't understand right now at all. And actually, it'll give us definitive evidence for intermediate mass black holes, because right now there's sort of called a mass desert. I think between like a few hundred solar masses to like 50,000 solar masses, there isn't a single confirmed case of a black hole. There's a lot of work to be done, and LISA is going to do a lot of that in these sort of gravitational wave experiments. So yeah, it's going to be really, really cool once that comes online.
Oh, very cool. It kind of ties into something I was thinking, particularly when you talked about the possibility of rogue supermassive black holes flying out in space. We had a number of microlensing surveys out there. Do you know how off the top of your head what the highest mass black hole discovered via microlensing would happen to be?
That's a good question. I probably knew that a few years ago, because when I started in research as an undergrad, I was actually doing microlensing. But I don't know off the top of my head. That's a good question. I should jot that down for later, actually. Yeah, so I don't know the answer to that.
Okay.
Yeah.
Well, here's a question to a more theoretical, even more theoretical question, a cosmological question. Dalton asks, do you think every AGN has a second part to it, such as a white hole that spills everything out?
So this was a really fun sort of philosophical debate back when black holes were proposed and when they started to be discovered, because it took a long time. I think originally the paradigm used to be that in the early 1900s, people thought that, or astronomers thought that stars evolved, they became white dwarfs, and that was it. Chandra came along and showed that when you involve quantum mechanics, that the higher mass stars have to collapse and supernova. And so he showed they would turn into neutron stars. Then it was shown that neutron stars could also collapse into black holes. And it took about 30 years before people took it seriously that these things could exist. And it was still yet another probably 20 years or so before supermassive black holes were even hypothesized as powering these central regions of the galaxies. And so one thing people asked then was, well, is this material falling in and going somewhere? What's going on here? Could there be white holes where the material is spilling back out? And the conclusion we've come to is that there are no white holes. So there's only black holes. And so the reason there is for this is that if there was if you could imagine sort of these black holes being like a wormhole from science fiction, where the material's flowing and passing through space-time and coming out somewhere else, there'd just be a tremendous amount of energy exiting the other counterpart. And so these would be incredibly bright objects. They would be easily picked out in space. And they'd be as bright, if not brighter, than the brightest AGNs, or the brightest AGNs we call quasars, which are is derived from the word quasi-stellar, because they look like stars from a distance. And so these would be incredibly bright objects that would be easily picked out. So as exciting as an idea as it is, and I think it's been featured in science fiction too, as far as the evidence goes, there is no such thing. There is some work that people have done on like wormholes, which is still very science fiction-y, but people have written papers about it, and it's very interesting. But as far as that goes, as far as we're concerned, the material falls into the black hole and gets crushed down to an infinitely dense point called the singularity.
Not leaving.
All right, I'll leave in 1 minute.
Second. Whoop, I didn't mean to mute you there, Ryan. Thank you again. Are there any other questions that people might have for Ryan, our speaker? We have a question that says that white holes also violate the second law of thermodynamics. Is that accurate?
That's a good question.
I mean, would entropy increase, or I guess it would be decrease as material falls out of something?
I want to say yes, but I don't have a good reason as to why. Because I think I've heard this before too, and I've never actually taken it to heart before. But I think the answer is yes, but like I said, I don't have a very good answer why. I think maybe, well, one reason as to why it could be is that in order for the material to come back out of the black hole somewhere else, is that you would have to basically be, well, I guess this isn't the second law of thermodynamics, but you'd have to basically give it energy in order for it to climb out of the gravitational well. Because as light particles flow through a gravitational well, as they climb up out of it, they actually lose energy. So you'd have to provide energy for the light to be coming back out of this gravity well, assuming that it can make it, assuming that the other end of the black hole, if there was a counterpart, didn't also exceed, assuming that the escape velocity didn't exceed the speed of light. So as far as the second law of thermodynamics, I don't know. I don't have a good answer why, because the one I just provided isn't really a thermo answer. It's more of just a gravity question, or a gravity answer. But that is a good point. It's probably on Wikipedia. Most questions like that are, honestly. But I'm sorry, I don't have a better answer for you.
It does seem to violate the conservation of energy and matter.
Yeah.
In that you're right, it would seem as if as if energy needed to be created from somewhere that it wasn't before. So I would agree with you in that. It does. I would also say that yes, that does violate the second law of thermodynamics, but I don't have the best explanation as to why. It's more of a gut intuition.
Yeah.
So, unless there are any other questions, we can transition to our the public night aspect of our public night, the telescope tour of our public night. So Ryan, if you'd like to hang around and watch that, you are more than welcome to do so. And before we do that, though, I'd like one more round of applause for Ryan. Again, it's an excellent talk, and thank you for all of the questions that were asked. They are very, very much welcome.
Thank you so much, and thank you for the questions. Really, really great questions.
Okay. Kevin, it is your show. Take it away.
All right, just a moment. Okay, can you see this webcam view here now?
Yes.
Excellent. So welcome everybody virtually to the GMU Observatory. As was mentioned at the start of the event, due to overcast skies, we will unfortunately be having what's called a closed dome tour. So we're not actually going to open up and get a live view of what's happening in the sky. But we'll still show you some images of some objects that we have looked at before with our campus telescope. And we definitely do invite you guys to come back sometime soon when the weather's a little bit better, whether that's a couple weeks from now or sometime next semester. And we'll get a good view of something in the night sky. So as you can see here from these webcams that are set up on the roof of Research Hall, here is our campus observatory. Here in the top left, we have the star of the show. This is our 32-inch research telescope. That 32-inch number refers to the aperture of the telescope, which is the size of the opening in the tube and the size of the primary mirror on the back of the telescope. The optical design of this is called a Ritchie-Cretan Cassegrain reflector, which is basically just a fancy name for how the mirrors are arranged. It's a pretty common optical design for research telescopes, such as the Hubble Space Telescope, which was mentioned before, also uses similar design. And so basically how the light travels is it enters from the sky through the front of the telescope, as you would guess, and it bounces off the large primary mirror in the back, which then bounces back up the tube to a smaller secondary mirror, which is about 1 foot across, which focuses the light further and bounces it back in through a hole in the center of the mirror before being reflected one more time into either the eyepiece or one of our various instruments on the back of the telescope. And let's see, I will put in the chat the optical design. There it is right there. Yeah, I see. Okay, it's in there. Great. Here in the top right, we've got a live view of the control room where we would be if we wanted to control the telescope in person. We're actually remotely controlling the operations computer, which is on the black desk on the left-hand side there, which is where up until the pandemic, basically we had to be in order to operate the telescope. One silver lining of everything going virtual is we did have to adapt rather quickly, and we are now able to control everything completely virtually from the comfort of our own homes. In the bottom left, we've got an outside view of the dome, which protects the telescope, obviously, and we open it up. We open up a shutter on it to actually look out the night sky. For reference, the dome's about 20 feet across or so. The door there is normal door size, about 6.5 feet. And then this bottom right wheel looking assembly is one of the 2 motors that we use to actually point the telescope at things. You can see there's another on the top of this fork here in the telescope view that points the telescope sort of up and down in the sky. And then this bottom right view twists the fork that the telescope is mounted in. And between those 2 axes of motion, we can point pretty much anywhere in the sky. Let's see. So as I said, we're not going to be able to get a live view tonight, but we will show some images that were taken with our CCD camera, which is the instrument we use for astrophotography, as well as some research observing. That CCD camera is about 4,000 pixels by 4,000 pixels. It gives us a field of view of approximately 26 arc minutes, which is a little under half of a degree. for kind of a context of what that means, it's a little bit smaller than the size of the moon on the night sky. So when we point at something, that's essentially the field of view we're getting from our research camera. Let's see, I will, let me open that up. All right, here is a post-processed image of what we have been able to capture with our research telescope. What we're looking at here is called the Fireworks Galaxy. It's about 25 million light years away from the Earth. And it gets its name, the Fireworks Galaxy, because it actually has the most observed supernova of any galaxy that we've seen in the universe. For reference, the Milky Way galaxy is shown to have about one supernova every 100 years or so. And in the last 100 years, this Fireworks Galaxy has exhibited around 10. So that's why it gets its name. There's a lot of cosmic fireworks happening within it. We are going to stay galaxy themed, I think, based on Ryan's talk. And you can see these blue outer arms of the spiral as we're looking edge on the spiral galaxy, the same structure as our own galaxy. These blue areas are regions of star formation. The younger, bluer stars are what's giving it that color. I think from here, I'm going to turn it over to M, the other observatory TA, for a bit to look at a couple more objects. And while he does that, I will look into the chat and maybe answer some questions via text.
Hello. Okay. So I'm going to take over from here. Right. The next subject we're going to look at is M33. So when we capture this image, it's in black and white or monochromic. I'm not sure which filter we use, but eventually when we combined with all the filtered images, we ended up having a nice picture of this object. So this is a galaxy. It's called M33. M is for Messier. It's a name of French astronomer who invented a catalog for something faint in the sky. The common name of this object is called triangular galaxy. It's because it's in the constellation of Triangulum. For the general information about this galaxy, it's about 2 or 3 million light years away from us. And it's in our local group or our neighborhood galaxy, along with Andromeda galaxies and small and large Magellanic Cloud galaxy. I think I can show you the location. So we use this software called SkyX to control the telescope in normal operation, the open dome tour. So basically, when we want to look at an object, we just point it and we just command through this button, and telescope will slew or move to a particular point on the sky. So this object is M33. It's here, right at the edge of Triangulum constellation. It's close to Andromeda galaxy, as you can see here. But this is not necessary for the local or neighbor galaxy to be close together when we look at the sky. It just happened to be there. So this is close to Andromeda galaxy. And with this combined filters images, we can see some red and blue spots. I'm not sure the component of the filter again, but I assume that if there's an infrared picture in this, those should be a relatively new stars formation. Those red spots is where the new stars clustered. Okay, and according to our software, the location on the sky is about in the east. So if this were an open dome tour, we can look at it. If the light pollution is low enough, it's on the sky during this time of the year. And this is, we cannot see the clear structure in this picture, but it's actually a spiral galaxy. Actually, it's the smallest spiral galaxy in our local group. But because of the size is small, we don't believe that there's a black hole at the core or nuclei of this galaxy. Okay, the next object I want to show you is M51. There's a lot of version. I'll start with this black and white version first then. So this is taken by our telescope, but with one specific filter, which I don't know which filter. We tend to have some noises here. Probably it's because of the dust. So M51 or Messier object 51 composed of two sub-objects. So they are two galaxies. I think nowadays we specify that this bigger object is M51A and this is M51B. This one, M51A, has a common name which is called Whirlpool Galaxy. You can see the shape of it looks like whirlpool. And this one, M51B, has another name called NGC 5195. NGC is short for New General Catalog. It's another type of catalog. Astronomer named objects on the sky. So if we have multiple filters images combined, we can see it with this nice color. It's nice whether it's a true color or false color. Astronomer can use false color to tell the component of the galaxy, so it's useful anyway. But we don't know here what kind of filter we use. So the M51 or Whirlpool Galaxy, it's a spiral galaxy and it's pretty big. So we believe that there is a supermassive black hole at the core or nuclei of this galaxy. And the gravity is strong enough to distort the M51B galaxy to merge it with this galaxy. So it gave this M51B an irregular shape. We cannot clearly classify it, whether it's a spiral or an oval. It seemed to be distorted by the gravitational pull. And they are about, though they seem close together, they are about 25 million light years apart. Those galaxies are in the constellation called Canis Venatici. I'm not sure I'm pronouncing it correctly. It's close to the constellation Ursa Major, which I believe it's set already. Yeah, it's around here. This is Ursa Major, and this is Canis Venatici. Yeah, it's at the horizon, so we cannot see it during this time. But perhaps if we were to look at in the dusk, we can see it close to horizon during this time of the year. What's special about this galaxy is it's a Seyfert galaxy. The Seyfert galaxy is a galaxy that emits bright light and also some intense electromagnetic radiation. In this case, this type of Seyfert it emits infrared, and we can use it to study its spectrum and to study its relative motion to us, redshift or blue shift, by looking at the spectrum, probably the radio wave or somewhere in far infrared region. Okay, so I think that's all I have. I will switch back for Kevin, and I'll be happy to take any question too.
All right, we did get a request in the chat to have another look at the fireworks galaxy, which I totally understand because it's an awesome image taken by one of our undergrads who is very into astrophotography. I want to also put out a reminder to anybody that's interested in this sort of stuff. For our student organization photo, Friends of the Observatory, they do have photo nights pretty frequently, probably every couple of weeks, where they do get to use our campus telescope on clear nights to go look at interesting things in the sky. They also do some stuff with astrophotography like this, where you learn a little bit about how these images are actually taken and made. And they seem like a pretty active club. You can find them on Mason 360, or also they have a student-run Discord that you can probably find in the GMU Discord hub. And an interesting thing about this image, you can see in the file name, it says 90 minutes. That's actually how long, over how many exposures that we're collecting light. These objects, as a reminder, they look really bright in these images, but they are very, very, very faint. You definitely can't see them with your eye, even looking through the eyepiece. And so you need to take multiple exposures with the camera over and over and over again to continue to basically accept photons into the detector. And you can stack many images on top of each other to bring out finer details in otherwise really, really faint objects. Let's see. All right. Well, if there are any further questions, feel free to ask them in the chat. Otherwise, I think that's about all that I have. And I suppose that will conclude tonight's evening under the stars.
I did want to mention you're talking about photo. Photo is having their a meeting tomorrow, actually. And if I'm not mistaken, it starts at 6.
I can go double check real quick.
All right.
Yes,
if you
tomorrow 6 to
have
7.
6 to 7.
I believe it'll be in Exploratory Hall 3301.
Yes, that is true. So just wanted to point that out before we end tonight. But and thank you, Kevin, for the excellent telescope tour. Having a hard time with words tonight for some reason. All right, so yeah, thank you all for coming. And we apparently have a request for one of the images that can be used as a signature to my my assignment. So
Sure, I'll pull this back up.
that is the firework galaxy.
Yes.
Kevin, when will the recording be available?
Oh, I don't know.
I believe it usually takes about 5 to 7 days, about a week.
Soon TM. Let's see, a request for the whirlpool. I can pull that up again too. Let's just.
Real cool is one of my favorites. M51.
Yes, it is a nice one for sure. There we go. This is actually, it looks like maybe a different one than we looked at before, but they're all good.
M51 was the second object I attempted to image in the night sky using astrophotography with a small aperture telescope. Well, small aperture telescope.
Cool.
First was the Orion Nebula. So,
There was a question in the chat if the firework galaxy had a Messier number, and I don't think that it does. I think if it did, it would be fairly easy to find, and I didn't immediately see it. So it might not.
yeah, I don't know if it has a Messier number either. But, oops. All right. Well, unless there are any other requests, we're going to sign off for the evening. Please enjoy the rest of your evening. And if you're any of my students, please, well, for all of you, please enjoy the weekend.
All right.
Thank you.
Bye-bye. All right, I'm signing off.